Hello everyone, I am Juvannie Alquizar, and in this video we are going to talk about the dining philosopher's problem. So for an introduction, the dining philosopher problem is basically a representation of processes that are sharing the same limited resources. So for this problem, I have already created a program to solve this problem. As you can see right here, for an overview, this program actually is dependent on the position of the philosopher. So let's say, for example, if the philosopher is in odd position, or if his position number is equal to 1 or the odd numbers, then he must take the left chopstick or fork first before proceeding to the right chopstick. So if his position isn't even, then he must take the right chopstick, then left chopstick. So right now we are going to read this code. We have to initiate a integer array for the position of the philosopher, and and one semaphore variable mutex and an array of available forks semaphores. I have to actually create a 5 semaphore for our chopsticks, or in this case I call it forks, because there are 5 philosophers. So to start this code, we are actually going to read the main function first. So this int I is used for the for loop. It's nothing new. We have to actually declare an array of threads because there are 5 philosophers and each of them represents a single process. After that, we are going to declare, or we are going to initiate the mutex semaphore with 1 as our argument, meaning that this mutex is actually open right now. And next, we are going to initialize the array of avail fork semaphore, and we have to make it open as for the initialization. Then we are going to create the 5 threads that will take the philosopher as its function, and the fill I, this is the position which we declared earlier for the philosopher, as an argument. Then we are going to just join all of this thread to make sure that the program won't end even if another thread is still running. As you can see right here in the philosopher function, which is a function for the parameter of for our thread, we have an infinite loop, and we actually created a integer pointer that is pointing to the void number pointer. Well, this actually enable us to access the value of our parameter. Now, as I said earlier, this program is dependent on the position of the philosopher. So in this if statement, we are going to check if the position of the philosopher is even. So if not, then it will go to this part of the program. So in this part, we are going to actually call in the function and pass in the argument integer I, or the pointer I, and proceed to this part of the code. So for synchronization purposes, we are going to use the simwait and mutex. So in this part, we are going to, or the program will actually lock the mutex, because we'll lock the mutex and proceed to this part of the program. Well, by locking this part, it will hinder the consecutive processes that will access these resources as long as it is not posted or it is not released. After that, we are going to print out philosopher %t is hungry. Then, since we are going to take first the left because the assuming that the philosopher is in odd position, then first we are going to take the left chopsticks first. So we are going to lock the chopsticks at the left, meaning that it is taken by the philosopher percent D. Let's say for example at this case, let's say for example philosopher 1. Then after that we are going to take the we are going to take the chopsticks on the right. So this same weight function will enable us to check if the right chopsticks of the current philosopher is available. So if not, then the program or the process will stay right here up until the avail fork semaphore or the right chopsticks is now available. So if that's the case, it will proceed to this part, which is it will print out that the current philosopher has taken that number of the fork or chopstick. Then we are going to release the mutex semaphore to enable the other processes to proceed. And then after that, since we have already taken both chopsticks that is needed for the philosopher to eat, it will call in the eat function, which is right here, and it will print out that the philosopher is eating. So for 2 seconds, the philosopher will eat. After that, it will release the fork. So by releasing the fork, which is right here, we have to print in the philosopher is thinking, meaning he has already eaten and now he is thinking. After 2 seconds, then the philosopher will now release both of the chopsticks or forks that he have been using. For after releasing that, it will now be available for the other processes or the other philosophers for use. So to put this in action, we have to compile this using the terminal. And we have going to minimize just this and open up the terminal and type in gcc and philosopher.c and hit enter. As you can see right here, a file a.out has been created. So to open up this output, just type in / then the name of the output and hit enter. You have just to wait a bit longer so that we can actually test the output. This program is actually an infinite program, as I said before, so it will keep running infinitely. So at this point, it is now clear that the output has been looping and looping, so we just have to close it like this. Now if we are going to analyze the output, at the first 5 lines they are thinking. Well, this is actually obvious because at initiation stage they are actually thinking first. Now right here it says that the first philosopher that is going to is hungry is philosopher 2, since all of the forks is now available because no other than philosopher 2 is hungry, then he can freely take his left and right chopsticks, which is right here. So at this part, the other processes or the other philosopher should not take these 2 forks right now because it is now in use by philosopher 2. After taking these 2 forks, he can now proceed to eating, as you can see right here. After this eating, you can see that philosopher 3 is hungry. So philosopher 3 is right next to philosopher 2. So in this part, philosopher 3 should not take the chopstick that is taken by philosopher 2. However, right here, philosopher 2 is now already done thinking, or is now thinking, meaning he is already done eating, and he already released the fork that he used. So by taking that into an argument, then then the fork 2 is now available for philosopher 3 to use, and fork 3 is also available for him to use. After that, he's going to eat because both of the forks is now available for him. Then he's going to eat. Then next, you can see that the philosopher 4 is hungry. Then, since the fork 4 is available, he takes the fork 4 first. After taking the fork 4, philosopher 3 is already done eating, and now he is thinking, meaning the fork 2 and 3 which he has taken before is now available for use to the another philosopher. And since it is already available right here, then philosopher 4 can already take the fork 3 right here, so that he can proceed to eating right here. After that, philosopher 5 is now hungry, and actually after then philosopher 4 is already done eating, and meaning he released the used fork, and philosopher 5 has taken both of the fork available. Then the cycle repeats, and philosopher 5 is eating, then philosopher 1 is hungry, philosopher 5 is thinking, meaning he released the forks, and philosopher 1 has taken both of the forks, and then philosopher 1 is eating, then philosopher 2 is hungry. Then philosopher 2 has taken fork 2, meaning he can right here he cannot take fork 1 because philosopher 1 is just eating or is currently eating, but right here philosopher 1 is thinking or is done eating, then the fork 1 is available for use, which fork 2 has taken it to use for eating. As you can see, at this output proves that there is no deadlocks to our solution, and there are no overlapping of forks used by the philosophers. That would be all. Thank you for listening.